Alrighty, welcome to day 4, High Performance State Ingestion and Automated Anomaly Detection. Mission briefing for today is that your objective is to build an in-memory network connection tracker and anomaly detector. Imagine a firewall under distributed brute force or denial of service attack, spitting out hundreds of thousands of log lines per minute. You need to ingest this stream in real time, build a high-performance state table, identify the top offending IP addresses hitting your block list, and maintain a rolling window of the most recent critical security events. The concepts that we are going to learn today is in-memory state aggregation, hash table mechanics, the double-lookup tax, automated factory initializers, Max-Heap priority sorting, contiguous versus linked memory layouts, and pointer-linked sliding windows. The first pillar that we're going to talk about is the key error tax and defensive state initialization, the clean code aspect. So standard Python dictionaries are highly efficient, but they are strictly reactive. If your code attempts to access or modify a key that does not explicitly exist yet in memory, the Python interpreter immediately halts execution and throws a key error. The danger is that the double lookup pattern, when passing millions of firewall logs, many engineers write defensive verification checks to avoid crashes. However, this introduces massive computational inefficiency. So this is an example script where the first line it checks if the key exists, the second line initializes if the key is missing, and the third line retrieves lists to append. However, across a multi-gigabyte infrastructure dump, executing 2 to 3 separate hash table lookups for every single log line introduces a massive unnecessary performance penalty. So the line-by-line breakdown is the first line, if src_ip, not in connection_matrix. What it does is that it checks if this specific IP address has been seen before by looking it up in the dictionary, so connection_matrix. The performance hit, lookup 1. So Python has to search its internal memory structure to see if this key exists. Connection_matrix in square brackets src_ip equals to open and close square brackets. So what it does is if the IP is completely brand new, this line runs to initialize it, it creates an empty list and assigns it to that IP address so we have a place to sort ports. The performance hit number 2. So Python has to search the memory structure a second time to insert this new key and its empty list. The third line is connection_matrix src_ip in square brackets dot append this underscore port. So what it does is now that Python is certain the IP exists in the dictionary and has a list attached to it, it grabs that list and adds or appends the target port number to it. So the performance hit lookup number 3. So Python searches the memory structure a third time just to retrieve the list so it can append the port. What is this called? Why is this called rather the double lookup tax? So if an IP address is already known to your script, which happens millions of times when a single IP hits your firewall repeatedly, Python still executes line 1, lookup number 1, and line 3, lookup number 3. So instead of looking up the IP address once, grabbing the list, and appending it, Python forces your computer's CPU to look up the exact same IP address twice per log line. Across a multi-gigabyte log file with millions of entries, this repetitive searching creates a massive bottleneck. So the solution is collection.defaultdict. A default DICT completely bypasses this validation layer by taking a callable factory function such as list, set, or int upon instantiation. How it works is that when a non-existent key is accessed, the default DICT automatically invokes the factory function, creates the default value, and links it to the key and returns it. So essentially it merges the 3 call-ups that we touched on before into one step. The performance edge is that this entire routine happens natively inside an optimized single-step C-level operation under the hood. And this is the example of the code in action. So from collections, import default DICT, connection_matrix equals to this with list. And then you do connection_matrix, src_ip in square brackets, append destination port. The next thing I'm going to look at is hash tables and the mechanics of counter, the scale aspect. So to process telecom-grade log arrays in real time, the scripts must maintain an absolute constant processing speed regardless of whether you have processed 100 lines or 10,000 lines. The theory is constant time versus linear time. So the wrong way would be linear time. So if you track IP frequencies using a standard nested list or array, the CPU must scan the entire list element by element to locate and increment an IP's tally. As the list grows, the script slows down linearly. The right way is the constant time, which Python dictionaries and counter objects utilize a hash table architecture in order to accomplish. A cryptographic mathematical hash function converts an immutable key, so unchangeable, like the string representation of an IP address, directly into an integer index corresponding to a specific bucket in memory. Because computing a hash takes an identical amount of time, whether the table contains 1 item or 1 million items, insertions, lookups, and updates run in constant time. So I've just written down an analogy to help simplify this for you. So take the sticky note stack. This is linear time. So imagine you write down every blocked IP address on a separate sticky note and stack them randomly on your desk. The process is when a new packet comes in, you have to read the top sticky note. If it's not a match, you flip it over and check the next one. You have to repeat this line by line down the entire stack. The scaling problem is if you have 10 sticky notes, it takes a few seconds. If your firewall experiences a massive attack and spits out a million logs, your stack is now a skyscraper. Finding a match requires searching the whole stack time it takes grows perfectly in a straight line with the number of logs. The PO, post office box wall, is the constant time analogy. So imagine you have a massive post office wall with numbered mailboxes. You have a master rule, a hash function that instantly converts an IP address into a specific mailbox number. So this IP address, 192.168.1.1, maps to box 405. The process is that when a packet arrives, you run its IP through the rule, get the number 405, walk directly to that box, and look inside. The performance edge is it doesn't matter if the post office has 10 mailboxes or a million mailboxes, because you know the exact destination immediately. You walk straight to that box, and it takes the exact same fraction of a second. The scale of the network doesn't slow you down. It is constant time. So this is where the advanced optimization, counter.most_common, comes in. So when extracting the top 5 offending attacker IPs out of a pool of 1,000 unique addresses, an amateur script will sort the entire dictionary. Sorting is computationally expensive, taking 0 to k log k, where k is the number of unique IPs, and I'll have an image just to represent what that looks like. The counter.most_common end method optimizes this by deploying a Max-Heap priority queue algorithm under the hood. So what does this mean? That instead of sorting every single unique IP in memory, it tracks only the top and highest frequencies dynamically. This dramatically scales down execution complexity, ensuring that your workstation CPU handles high volume triage without breaking a sweat. And this is what you have: the constant in green, you have the linear in blue, and you have that log linear time in red, just to illustrate what I'm talking about. The next pillar that we're going to look at is continuous memory arrays versus pointer-linked blocks, the memory optimization aspect. And this was a really cool concept that I learned. So just stay tuned, and hopefully this begins to make a bit of sense. Maintaining a rolling seam ticker or a sliding window buffer of the latest security events introduces a fundamental architectural choice: how data is laid out inside your system RAM. The overhead problem: contiguous memory shifting. A standard Python list is implemented as a dynamic array. Elements are packed directly next to one another in continuous blocks of physical memory. Just for a definition, contiguous means touching, adjacent, or sitting shoulder to shoulder in an unbroken sequence. The front popping trap. Appending an item to the end of a list is incredibly fast. However, if you attempt to keep a rolling window of 100,000 logs, for example, by removing the oldest entry from the front via list.pop, every single remaining element in the array must be copied and shifted exactly one slot to the left. The impact is that for a high-speed log parser, this forces the CPU to perform millions of memory copying operations every second, rapidly inducing kernel sluggishness or process freezing. And I've got an analogy to explain this as well. The solution is collections.deque, double-ended queue. A deque treats memory entirely differently by utilizing an internal structure composed of blocks of doubly linked lists. So the advantage is that elements are not restricted to contiguous memory addresses. Instead, each data block contains the actual security log payload along with 2 tiny tracking tokens. They point to the previous block and are pointed to the next block. So it's true O1 performance, with O1 being constant time. To push a new alert onto the back or drop an old alert off the absolute front, pop left, the engine never shifts data blocks. It simply alters the memory pointer addresses of the outermost boundary blocks. So just the analogy, we have the couple train analogy. So instead of a row of houses built into concrete on a street, which represents contiguous memory, imagine a freight train out on the tracks. Each train car represents a separate block of memory holding your log data. The cars aren't welded together into one solid giant piece of metal. Instead, they're held together by couplers, which act as your memory pointers. So every car in the middle has a front coupler connecting it to the car ahead of it, the previous pointer. Every car has a rear coupler connecting it to the car behind it. Hopefully you can imagine this. So why adding or removing from the ends is constant time. So imagine your train has a strict limit of 10 cars. Your max length is equal to 10 threshold and is currently full. A brand new security log car rolls up the back of the train, meaning the oldest car at the very front needs to be dropped. If this were a standard Python list, you would have to lift up every single train car and physically slide it down the track to close the gap. But with deque, the train conductor does 2 simple things. It uncouples the first car, walks to the front, pulls the pin of the coupler between car 1 and car 2, and lets car 1 roll away. Car 2 is now the official start. Whereas now the new car at the back, the conductor walks to the very back, backs the new car up to car 10, and drops the coupling pin into place. The conductor never has to move, slide, or lift the heavy train cars in the middle. Whether the train is 10 cars long or 10,000 cars long, uncoupling the front and hooking up a new car at the back takes the exact same fraction of a second. That is true constant time performance. So this is another side note. By initializing a deque with a strict max length attribute, for example, max length of 10, the C-level engine handles this pointer swapping automatically the exact moment your threshold is crossed, providing a bulletproof, hard-capped memory boundary. The final pillar that we want to talk about is exact structural validation versus state abstraction. And it's just a template or table to discuss the 3 main topics that we went over earlier. So we had default DICT, list/set, we have counter, and we have deque, max length x. Take a moment to read this, but it just essentially covers what I did earlier. but this table just helps break down and clarify the internal structure, what it's best developed for, and the core time complexity. So take a pause and read through this. Moving on to the pseudocode. To set up something like this, you want to set up the memory trackers first. So you want to have rolling underscore alerts with a window holding only the last 10 security alerts. You want to have IP underscore counters with a tally counter to track how many times each IP is blocked. And you want to have attack underscore tracking to link to a map linking each bad IP to the unique ports it hit. So before I look at the code, I just want you to try and map out which of the data structures fits to each of the memory trackers that we're going to be doing in just a moment. So if you've understood the concept properly, so you should be able to understand the correlations between the three. Then we have the function processes for each line in all log underscore lines. If it has system alerts, you add a line to rolling alerts. If it has a denial block, you find the IP and the port in the line. So that's IP counters. And then if IP is found, you add one to the tally counter for this IP. If a port was found, you record this port under the IP's name. And then you have the rolling alerts. You print the top 5 most frequent IPs from the counter. For each IP inside attack underscore tracking, if that IP hit more than 20 unique ports, you print horizontal port scan alert for this IP. Now, in exactly a few seconds, I'm going to go over the final code. So if you want to pause now and give this a run for yourself, you can do that. Cool. Now, going over the full final code, what it looks like. We start with just importing the counter, default, DICT, deque, RE as well from the previous day 3, and then we also have collections as well. So we have this first part here. Essentially what it does is the pattern targets standard IPv4 addresses while avoiding performance traps. So we have the word boundaries, we have this octet loop, and we have the final octet. I went over it more in deep dive in the last daily challenge, day 3, but here's just, if you want to pause and have a read, it will make sense, but I go into further, more precise detail in the last video. And then this second line is for the port pattern. And we didn't really touch on this last video, so I'll touch on this again. But this first line is the prefix match. And it's a non-capturing group that looks for either the text DST port or a literal colon. This tells Python, look here, the port number is right after this. Okay, and then this is the actual port number. Then we just define process underscore logs, all underscore log underscore lines, and then we have the rolling alerts is deque, we have the IP counters as counter, and then we have the attack tracking as default DICT set. Now it's going to print processing log stream, and then this part here for line in all log lines, we have the line strip. What this does is that it loops through your log source line by line, removes trailing white space or new line characters. We touched on this in day 1 challenge, why this is important to do, but essentially ensures your spatial complexity stays locked at unique bad signatures because it processes data sequentially without reading massive log chunks into memory at once. This next part is pretty self-explanatory, so you can just have a look. But essentially, if I go to part 2, the sliding window security tracking deque, what it does is it's a lightning fast substring check for sysalert. If found, it appends the entire log line into rolling alerts. Because rolling alerts was initialized as a deque max-length 10, this step uses a pointed alteration. If there are already 10 items in the queue, adding a new alert to the back automatically slides the oldest alert off the front of the train car, keeping a hard cap on memory. So you can see, we define the max-length 10 up here. So part 3 is the state tracking and the default dictionary / counter pipeline. So what it does is if a line indicates a blocked connection, it uses your regex engine to look up for an IP address. If an IP is found, we have this command here, which increments its block count. Because IP underscore counters is a counter object, this hash table lookup and math addition runs in constant time, which is this part here. Now we're going to have the port match, which is the same part 3. So within that same block, it immediately runs the second regex to isolate the destination port number. It converts the extracted string digits to an integer, bypassing the key error tax. It takes that port and drops it directly into the attack underscore tracking mapping. Because attack underscore tracking is a default dictionary set, you bypass the manual check step entirely. If the IP is brand new, an empty Python hash set is generated natively in C code, and the port is instantly tossed inside. Part 4 is right here. Once the main file loop concludes and the stream finishes, the script prints out your final security analytics, loops over your deque block links to display the final 10 high severity system alerts captured during the run. Which is this bit here. Now this next bit here utilizes a Max-Heap priority queue to pull the 5 heaviest hitters out of your counter table. It avoids sorting your entire dictionary database, shielding your CPU from a steep computational penalty. The next bit iterates through your attacker portfolio. Checking the length of hash length ports is a direct O1 property, constant time property. that check because Python tracks its element size dynamically. If a unique threat actor has touched more than 20 distinct points, it prints a critical warning flagging them for a horizontal network reconnaissance scan, which is just this bit here. So then we have the define get sample data. This is just part of the script in the simulation and testing environment. So it doesn't analyze real corporate log files. Instead, it generates synthetic predictable firewall traffic and memory so it can immediately test and demonstrate that your data structures are processing data exactly as designed. So it's just simple tests. The random function is a standard library module used later to pick random ports and regular internal IPs to simulate noisy network and background traffic. We have the test underscore IPs, which is a pool representing harmless internal corporate devices, generating basic connection blocks. We have scanner underscore IP, which is a specific IP address simulating an external malicious threat actor, executing a broad network sweep. And then we also have logs equals to open and close square brackets, which is an empty list that will hold all the mock text strings we generate. Random, test IP, scanner IP, and logs. This final bracket here. This script runs a loop from 0 to 99 for I in range 100. It uses basic modular arithmetic to split the traffic into 3 distinct types. Type A is the critical system alerts if I modulo 15 is 0. So triggered when the loop index is perfectly divisible by 15. So at 0, 15, 30, 45, 60, 75, and 90, this happens exactly 7 times. So it generates a high severity message, system alert, failed admin login attempt. Test purpose, this validates that your deque maxing 10 functions properly. Since only 7 alerts are generated, all 7 should survive and print out the final report without any getting evicted. The threat actor, horizontal scan, else if I modulo 3 is equal to 0. If it's not a system alert, this triggers whenever the index is divisible by 3. A lot more numbers, 3, 6, 9, 12, 18, etc. So the log line creates a line containing block, uses the malicious scanner IP, and systematically increments the port number. Destination port is equal to 100 plus I, e.g. port 103, 106, 109. So because this single IP targets more than 20 unique sequential ports, it is designed to explicitly trip the if length ports is greater than 20 threshold in the script, providing that your default dictionary set horizontal scan detector works. Type C is the standard firewall noise. So the match for all other lines that don't match the criteria above, the log line creates a line containing deny, randomly selects one of your harmless test IPs, and randomly assigns it to port 22, 80, or 443. So this is for the test purpose is to generate distributed background noise to populate your counter table, testing its ability to isolate the real high-frequency threat actors from normal network traffic. Very final thing I want to touch on, which is what I touched on in the last episode as well, is why we have this bit at the end. So this is just standard Python design pattern. It ensures that this file only runs if it is executed directly as a script. For example, double-clicking it or running Python script.py in your terminal. It calls get underscore sample underscore data to build a list of 100 fake lines. It passes that list directly into process underscore logs, running your analysis tools and immediately printing your visual security dashboard to the screen. So I'm pretty sure that is all for today's lesson. Just to recap, we touched on high performance state ingestion and automated anomaly detection. Each day we build up on the previous lessons. I will definitely be adding this to the GitHub in the next few days, so just stay posted for that. If I haven't, just leave a comment just to touch on based on what's going on, but I should definitely have that in the next few days to 1 week maximum. And I look forward to seeing you on day 5.